Section 2.4 is on page 179 in the book. It talks about continuity, and we have one definition on continuity, which states a function f is continuous at a point or a number a if the limit as x approaches a equal f of a. Now, in case you missed it, that's simply the y value when x equal a. Well, three things must happen for a function to be continuous at a point a. One, f of a must exist, and again this is the y value. The limit must exist. That means the limit as x approaches a from the left of f of x must equal the limit as x approaches a from the right of f of x. And the third thing, whatever this is must equal that limit, and that's what this definition is saying. So the easiest way to start this, you start with verifying this first. Is the y value present? After that, does the limit exist? And the third thing, are they equal? So example 1 right there says, given the function f, this is f, state the intervals where f is continuous. Well, we're going to say f is continuous everywhere except, and let's see. Now, how do you figure out if a function is continuous? You trace the graph left to right. Every time you have to lift your marker off the paper or your pencil off the paper, the function is not continuous. If I start tracing this graph left to right, I notice when I get to -2, I have to go up there. I have to lift my marker off the paper and then come back. So automatically -2. I continue on, and when I get to this red asymptote, I have to lift my pencil off or my marker off and move to this side, and that means it's not continuous at -1. I know these colors are hard to see, and that's done on purpose. When I get to 1, I notice that I have to lift my pencil off the page or marker and jump up there, and by doing so I know that it's not continuous at 1. And when I get to this point, I have to jump again, lift my marker off the board and go to that point. That means at 3 as well. Now those have different names. So whenever I see a vertical line there, so whenever I'm approaching infinity from one side or the other, I say that's an infinite discontinuity. Whenever I have a point, just a point, whether you put it there or you take it off completely, we say that's removable. You remove the point. Either you picked it up, moved it above or below, or you pretty much just wipe it off completely. Either way, that's called removable. And here, I notice here, the limit from the left and the limit from the right does not match. We call that a jump. Now, a jump discontinuity cannot be fixed, but a removable could. So here we are. The following types of functions are continuous at all numbers in their domains. Well, polynomials are continuous everywhere in their domain, rational functions, root functions, trig function, exponentials, and logarithms. So these are the types of discontinuity. As you see, by taking a point off, we say this is a removable discontinuity. Here, the limit does exist. F of a exists, but they're not equal. Call this I, call this double I. We know that I does not equal double I because the limit from the left and the limit from the right is going to be whatever this y value, but f of a is up there. Here we have a jump discontinuity. Here we know that the limit as x approaches a of f of x does not exist. Why is that? The limit from the left is going to give a value, and the limit from the right is going to give a different value. So we call that a jump discontinuity. And an infinite discontinuity, obviously, if you take the limit as x approaches a from the left, you get infinity. And the limit as x approaches a from the right of f of x, from the right, that's negative. And of course, the limit doesn't exist, but in this case, if you get infinity or negative infinity, automatically we say that's an infinite discontinuity. So they give us some problems. This is in the book on page 191. It says for the following exercises, determine the points if any, at which the function is not continuous. Classify as a jump, removable, infinite, or other. But let's see. If I look at this problem, I notice this is continuous everywhere. So no harm done there. This is really, so I know this is not continuous at t equals 0. And if I take the limit as t approaches 0 of 1 over t plus 1, if you remember the shortcut, we said that's infinity. So we say that's an infinite discontinuity. Okay, and if we look at the next problem, well, I notice this is t plus 3 divided by t plus 3 into t plus 2. These cancel out. But as it is, I already know that f is not continuous at t equal negative 3 and negative 2. Well, we canceled the 3 out, which means if I wanted to graph this, I'll be looking at y equal 1 over t plus 2. That has a vertical asymptote at negative 2, horizontal at 0. The graph passes through the point. If you put 0, you get a half. So the graph looks like this. So what do we notice? They're talking about where is this not continuous. Now, did you notice that the point negative 3 is not on the graph? So if you put negative 3 in there, that gives you negative 1, negative 1, negative 2, negative 3, negative 1. That's an open hole. So we know that t equal negative 3 is removable. And why is that? We were able to cancel it and we removed that point. But at t equal negative 2, if I substitute negative 2 in the remaining part, that will be 1 over 0. I know that's infinite. Again, what's left is f of t equal 1 over t plus 2. There's the graph. If I take the limit as t approaches negative 2, if I plug it in, I get 1 over 0. And we know from the shortcut of a limit, that means it doesn't exist. That means it's infinite, I'm sorry, which doesn't exist. Here, I know that x equals 0, so f is not continuous at x equal 2, the denominator equals 0. But here, you notice that absolute value is not included in those. Well, let's see. If we take the limit as x approaches 2 from the left, the denominator is x minus 2 all the time. The top, if the inside is positive, I don't need the absolute value. If the inside is negative, that will be minus x minus 2. Well, if you pick a point to the left of negative, to the 2, say you pick 1.9. If you put 1.9 in there, 1.9 minus 2 is negative. So to drop the absolute value symbol, you must put a minus in front of it. And that limit is negative 1. And we take the limit as x approaches 2 from the right. If we pick a point to the right, say 2.1, put 2.1 in there. 2.1 minus 2 is positive, so I really don't need the absolute value. That is 1. since the limit from the left and the limit from the right does not exist, we say this is a jump discontinuity. All right. Next list of problems. It's asking, decide if the following function is continuous. And again, we're only worried at the following point. If it is not continuous, say what type. Well, let's see. If we look at this, at pi, if I substitute pi in, I notice that that is 0 minus a negative 1 over 0. That's 1 over 0. Sin of pi is 0, correct. So wouldn't that be automatically infinite discontinuity? And I know this from the shortcut of a limit. When I'm going to take the limit as x approaches pi, don't you just substitute that in? And if you get it to be a number over 0, it doesn't exist automatically. And in this case, it's infinite because 1 over 0 is infinity. Here, so okay, well, let's see. First things first, does f of 1 exist? F of 1 is negative 1 plus 2, it's 1, yeah. And if I take the limit as x approaches 1, what would that be? Or here, if I take the limit as x approaches 1 of f of x, that would be, well, let's see. Limit from the left, I must use the top equation. That would be negative 1 plus 2, which is 1. Limits from the right, I have to use the 3x minus 6. That will be 3 minus 6, which is negative 3. So automatically here we say, well, that limit does not exist. Oops, it's the n. So what does that mean? That means it is a jump discontinuity. I get to the next problem. Obviously x equal 1, but if I factor that, well, that's what's left. If I was to sketch a graph of this, I don't have to graph, and you can never justify a problem by saying look at the graph unless you're given the graph. So if I ask you, hey, why is this not continuous? You can't sketch a graph and say look at the graph. That's not allowed. If I say graph this function, you'll say, okay, x minus 2, 1, 2, rise 1, run 1. So we know how that graph looks like. That's a line. But if I take 1, negative 1, 1, negative 1, that's an open circle. So we know that f of 1 is negative 1. We got it. I'm sorry. We say f of 1 is undefined because 1 is not in the domain. So there's nothing there. Therefore, f is not continuous. And that's removable. Whenever you could cancel it like that, we say that's removable. And this problem is asking, in the following exercises, find the values of k that make each function continuous. So we want this to be continuous. We want, and again, exponential is continuous ever on its domain. polynomial or linear equation are defined everywhere. The only point in question is if those overlap. So we want the limit as x approaches 4 of f of x to equal f of 4. So let's start with the obvious. What's f of 4? Well, f of 4 is e to the k times 4 or 4k. Okay, that's a value. How about the limit? The limit as x approaches 4 of f of x would be what? Well, let's see. If we take the limit as x approaches 4 from the left, we have to use the top function. And the shortcut, since this is an exponential, that's e to the 4k. The limit as x approaches 4 from the right. Well, from the right, you must use the x plus 3. And if you plug that in, that will be a 7. Now, what do we want? We want the limit to exist. For the limit to exist, we want the limit from the right to equal the limit from the left. That means 4k must be natural log of 7, and k must be natural log of 7 divided by 4. So when they say, for what value of k, we say, if k equals natural log of 7 divided by 4, f will be continuous. Over its domain. And that's it. That's really what you have to show. Now we have a theorem that's a really important theorem. I know to you it's going to say the obvious, but in mathematics it's a massive deal. Intermediate value theorem, since it's so famous, if you just write IVT, everybody knows what you're talking about. And it says the most basic stuff. Well, let's see. Make sure we understand what it says. It says that a function f be continuous. It's extremely important for you to say f is continuous. Otherwise, this theorem doesn't hold. Bounded by an interval between, let's say, a and b. If z is any value, so I take a, f of a, and I take b, f of b. If I take this value z, that happen to be between those two y values, then there must be an x. There must be an x between the a and the b, so that the y value at c is guaranteed to be between those two. Now we have an alternative. This is what we do. To really have this work easier for us, much easier. Otherwise, you have to show a lot of things. What we do, we take this and we say, take f of c minus z and set it equal to 0. So what we did, we subtract a z from each of those. If I subtract a z from this, that will become a 0. If I subtract a z from this y, and if I subtract a z from this, and this point right there will be right. And all what we have to do now, show that f of a is negative in this case, f of b is positive. And what do we know that there is between a positive and a negative? Automatically we know there is a 0 provided the function is continuous. Why is that? Because I can't move from a negative to a positive without crossing 0. That's the idea. Now the book doesn't have examples that I like, so I made up 2 examples for you. Here's one of them. It says, use the intermediate value theorem to show that there is a solution of the given equation in the specified interval. That's for the first part. The second one, let's say I didn't give you an interval. I'm going to take that one out. Okay. So here, in this case, I'll say, okay, well, let's see. And this is what I'm going to do. I'm going to move everything to one side. Instead of showing the two functions are equal, also I'll show their difference is 0. And that's saying the same thing. Oh boy, I forgot the x altogether. And what's so important about that? I'll say, look, if I take f of 0 is -1, that's less than 0. F of 1 is 1 plus 1 minus 1, that's 1, which is bigger than 0. So I start my proof by saying, first things first, f is continuous. You must state that f is continuous on the closed interval. Now this function is continuous everywhere. I just want to pick 0 to 1. Or you could say everywhere, that's okay, that's acceptable. But that's if I want to follow definitions, there it is. And f of 0 is negative. F of 1 is positive, as long as you show me those. So out of those, we know what? There exists a c in the open interval between 0 and 1 such that f of c equal 0 by the intermediate value theorem. And what's f of c? If this is my f of x, f of c is simply the square root of c plus c minus 1 equals 0. And you go back and show exactly what they want by moving that over. And there it is. And that's an official proof. Now, say they didn't give you an interval. You say, okay, where does cosine of x equal the parabola? Well, you say let f of x equal, and you move everything to one side, 0 on the other side. It doesn't matter which way you move those. Now you could play with that. You could say, okay, let's see, f of 0 is 0 minus 0 minus 1. That's less than 0. Very good. F of 1 is 1 minus 1 minus the cosine of x. And that is negative cosine of x. That's negative still. I'm sorry, that's x. 1. That didn't work. Okay, so no need for that. How about f of 2? So you could choose trial and error if you want. 4 minus 2 minus the cosine of 2. That is 2 minus the cosine of 2. And that's positive. How do I know that? The biggest or the smallest a cosine could ever be is -1. You take 2 minus 1, that's always positive. Once I establish that, look, it went between 0 and 2. I could go between 0 and 3. I go between 0 and 5. It doesn't matter. I could say, well, look, f, which is right there, is continuous. This will only hold if it's continuous on the closed interval between 0 and 2, right? And we showed f of 0 is less than 0, f of 2 is bigger than 0. And out of those, we conclude that there exists a number c in the open interval between 0 and 2 such that f of c equals 0. What's f of c? That is c squared minus c minus cosine of c equals 0. And then you look at the original, you want that on one side, everything else on the other side. And that pretty much finishes the proof. And that's pretty much it. That's what the section is about.